Welcome to the Ontario High School video podcast series. This is podcast 3 from Unit 10 of Chemistry, which deals with nuclear chemistry, and we're specifically going to address Learning Standards 10-5 and 10-6. Learning Standard 10-5 is simply this. I can define half-life and calculate the amount of radioactive material that remains after an integral number of half-lives. And when we talk about integral number, it's going to be whole numbers. After 1, 2, 3, 4, and so on, half-lives, how much would be left? Well, half-life is this. It's the time required for half of the starting material to be consumed. For radioactive isotopes, the starting material is often referred to as the parent isotope, and the new element resulting from the radioactive decay is referred to as the daughter element. So again, half-life, if you start with 100 grams of a sample, half-life would be the time it would take until you have just 50 grams of that sample left, and 50 grams of it has already decayed. So that's half-life. Half-lives can be calculated from measurements on the change in mass of a nuclide and the time it takes to occur. It is impossible to know specifically which nuclei will disintegrate or when they will disintegrate. The only thing we can precisely predict is that in the time of that substance's half-life, half of the original nuclei will disintegrate. The quantity of radioactive nuclei at any given time will decrease to half as much in one half-life. Here are some selected half-lives. So the isotopes, uranium-238 for instance, half of it will be gone from a sample in 4.5 billion years. In neptunium-240, half of it will be gone in 1 hour. Plutonium-243 is 5 hours. Americium-246 is 25 minutes. Californium-251, 800 years is the half-life. Nobelium-254 is just 3 seconds. Carbon-14 is 5,770 years. And carbon-16 is 0.74 seconds. Applications of half-life are very straightforward. The understanding of half-life allows for a process of radioactive dating. For example, in geology, rocks can be dated by comparing the ratio of the parent element, uranium-238 for instance in uranium, to its daughter element, lead-206. Dating organic material. An organic material is the material left over from living organisms that have died and begun the decay process. This can be dated using the nuclide of carbon-14. Carbon dioxide consumed by living systems contains a certain amount of, when you see this 14CO2, it just means that the carbon dioxide has carbon-14 as the carbon bonded to the oxygens rather than carbon-12, which is the more common isotope. So when you see 14CO2, it's just carbon dioxide with carbon-14 in it. When the organism dies, it no longer requires carbon-14, but the decay of carbon-14 continues. As time goes by, the ratio of carbon-14 to carbon-12 decreases by the half-life of carbon-14. So using these half-life equations, the time since the organism died can be calculated. A problem will demonstrate this. The half-life of radium-226 is about 1,600 years. How many grams of a 2-gram original sample will remain after 4,800 years? In order to solve this problem, we're going to set up a table that relates whole number integrals of half-life versus the amount of the substance, as demonstrated on the next slide. And we can find the total time by taking the number of half-lives times the half-life itself. So here's our table, and this works really well when we're dealing with whole numbers. Okay, the number of half-lives, we start at 0, and then we really choose the number arbitrarily. I chose to go through 4 half-lives here. It depends. You may need to go through more than 4, depending on what amount you have left over. But for our purposes here, 4 half-lives were enough. For our time at 0 half-lives, that's our original time, which is 0. At 1 half-life, it's 1600 years. 2 half-lives is 3200. 3 is 4800, and 4 is 6000. The amount of radium-226, well, at the beginning you have 2 grams. After 1 half-life, you have half that left, so there's 1 gram left. At 2 half-lives, there's 0.5 grams left, and at 3 half-lives, which is 4800 years, there's 0.25 grams left. Now, if we go on from there at 4 half-lives, it'd be 6,000 years, it'd be 0.125 grams left. But the problem asks how much after 4,800 years, and there it is, 0.25 grams. So after 4,800 years, which works out to be 3 half-lives, 0.25 grams of the original sample is left. Sample problem number 2, I'd like you to do on your own. And the way that you'll do this is to pause the podcast, write down the problem, and then set up a table similar to what we used to solve sample problem 1. And when you have solved the problem, go ahead and resume the podcast, and you can compare your answer to mine and see how you did. Welcome back. Let's see how you did. I went ahead and set up my chart with number of half-lives, the time, in this case in hours, and then the amount of plutonium-243. So you can see how the table is filled out. I hope that's how you did yours. And we were asking for how much of the, or how long it would take for just 12.5% of the sample plutonium-243 to remain. So I went through 4 half-lives on this one. I set up the time. Of course, at 0 half-lives is our time of origin 0. 1 would be 5 hours, 2 would be 10 hours, 3 would be 15 hours, and 4 would be 20 hours. And then the amount left. In the beginning, we start with 100%. After 1 half-life or 5 hours, there's 50% left. After 2 half-lives or 10 hours, there are 25% left. And after 3 half-lives, which is 15 hours, 12.5% of plutonium-243, the original sample, is left. So, looking at our table, we can determine that 12.5% of the sample would be left after 3 half-lives. The 3 half-lives times 5 hours would give us 15 hours total in order to get to that 12.5%. How'd you do? Let's look at applications of nuclear power, nuclear energy. 10-6 Learning Standard says this: I can describe applications of radioactive processes in areas such as energy production, military use, and nuclear medicine. In the United States of America, nuclear power plants produce about 19.2% of the electricity generated, and these are all fission reactors. Again, the hope is someday in the future that we'll have fusion reactors on board, because nuclear fusion gives off harmless byproducts, whereas nuclear fission gives off byproducts that have to be stored because of their potential harm. And also, the material used in nuclear fusion is much less dangerous than that of fission. It's just very difficult to get a fusion reaction going, and difficult to maintain that. So someday, hopefully in your lifetimes, you'll see fusion reactors come on board. In fire safety, smoke detectors have minute amounts of radioactive material in them. It's what is useful in terms of detecting smoke. So in terms of fire safety, radioactive material has great use to us. Among the most beneficial of nuclear applications are in nuclear medicine. For instance, iodine-131 is injected into patients to reveal images of the thyroid gland, as well as for treatment of thyroid gland diseases. Radiation treatments for cancer are another application for radioactive isotopes. One of the things that you want to look at, we had that slide before that showed the selection of half-lives. In medical applications, the isotopes that are used have very short half-lives, and you can see why you want to be able to use the isotope, get the positive effect from it, and then get it out of the body's system as quickly as possible. So in terms of radioisotopes used in medicine, they tend to be very short half-life radioisotopes. If you have heard of a PET scan, some of your relatives may have had one of these. It stands for positron emission tomography, and it's a type of nuclear medicine imaging. The radioactive isotope is inhaled, injected into a vein, or swallowed, and when the radioactive isotope is collected in the appropriate part of the body, the gamma ray emissions are detected by the PET scanner, which is also called a gamma camera, which works with a computer to generate special images providing details on both the structure and function of various organs. Here are some applications from the PET scans. They can be used to detect cancer. They can determine the spread of cancer. They can assess the effectiveness of treatment. They can determine the effects of a heart attack. They can evaluate brain abnormalities such as tumors and memory disorders, and they can map brain and heart function. So a few of the nuclear applications as it applies to medicine, which again have greatly benefited humanity. There are certainly nuclear applications for military use, the atomic bomb and hydrogen bomb. So a picture is worth probably in this case a trillion words, but this is a picture. The hope we all have, of course, is that never again in human history will this application be used, but certainly it is, has been and continues to be used in terms of military applications of nuclear power. Well, we are at the end of podcast 3. I want to leave you with a quote from the great physics professor Enrico Fermi. "Before I came here, I was confused about this subject. Having listened to your lecture, I am still confused, but on a higher level. I wish you well."